Thank you very much for the introduction. So I'll be talking about reverse engineering industrial control system binaries. And this is work that I did along with my advisor, Professor Magnetakos, funded by the Office of Naval Research. So industrial control systems are a little bit different from cyber-physical systems, and they target mainly they control and monitor physical processes that are found in industrial settings. Across a variety of sectors, you could have power networks, as we saw in the second speech. You can have nuclear plants, water treatment, desalination, etc. And this control happens with PLCs, programmable logic controllers. And on the slide on the left side, you can see the software development process for writing control logic for these controllers, for these PLCs. So process engineers, which is the equivalent of software developers in ICS lingo, would develop the source code for their control algorithms in one of the IEC 61131 languages. Those are, for example, ladder diagrams, which is visual language, or structured text, which is textual. And then pass this source code through an IEC compiler to generate binaries. These binaries would be then downloaded to the PLC, where a PLC runtime would take that and orchestrate it for execution on the PLC's microprocessor. And on the right side, you can see what the binary actually does. It goes through an infinite while loop that's called the scan cycle, where it actually gets the data in from sensors. So these are data for example, temperature readings, pressure readings, and then passes it on to the control algorithms that generate the calculate and generate the actuation signals to control this process. And those are written back to the actuators, closing this loop. Now, why would we want to reverse engineer these binaries, industrial control system binaries? And having this capability is a double-edged sword. So on the one side, we could use this to, for example, analyze malicious binaries that are found in the wild, for example, for PLCs. So probably you're familiar with Stuxnet that targeted nuclear facilities in Iran. So after finding Stuxnet, it was important to kind of understand what the binaries actually did. And there was a big race trying to reverse engineer that code. By proactively having reverse engineering capabilities, we could more easily and have faster incident responses to such cases. Another thing is to recover lost source code. So it happens more often than you would think that people lose the source code, especially in the case of legacy systems. So you have a PLC in the field that's been executing the same code for the past 20 years. Perhaps your facilities were targeted by a ransomware attack, so you lost the source code, and you want to figure out what the PLC is actually doing because you want to update it, for example, or you want to upgrade your system. So you could use reverse engineering to recover that source code. Now, malicious actors can also take advantage of reverse engineering, and they could use it, for example, to dynamically generate payloads, malicious binaries. And that is very interesting because it breaks the requirement for needing control and command and control servers, thus adhering to the requirement that many industrial systems have, or at least should have, for air-gapped communications. Now, when reverse engineering these binaries, we can and we actually should reuse a lot of techniques and practices from reverse engineering conventional binaries. However, these binaries also have some unique characteristics that makes them a little bit special, and we could take advantage of those to make the reverse engineering process faster and easier. So one of the things that's different is the execution model, the scan style that I mentioned, that is an infinite while loop. I can make differences when you're doing dynamic analysis, for example. And the second thing is the vast importance of I/O operations. So because these operations are very important, it's necessary to understand how these updates, read data coming in from sensors is happening, and also how data is written back to actuators. Now, something that can make life a little bit difficult is the fact that these binaries typically use proprietary file formats. So you won't have your typical ELF binaries for Linux or PE files for Windows. You probably have custom file formats for which you don't know anything about. However, on the plus side, usually these binaries don't implement any kind of optimizations. So the compilers don't do any implementation because of the fact that you have strict real-time requirements. Now, taking these different special characteristics of ICS binaries, we propose a structured methodology that consists of two phases to approach the reverse engineering problem. For the first phase, we target the reverse engineering of the binary formats, these file formats that I talked before, and then build some knowledge databases, particularly pertaining to two important things: the inputs and outputs, and how and where these occur in the binaries, and also a database that contains information about known library functions that are imported to these binaries, so to avoid reverse engineering the same thing over and over again. Since this is a one-time cost, given that there is a small number of platforms out there for ICS, this can be a manual analysis or semi-automatic analysis. And moving on to the second phase, this would consider the binaries, analyzing the binaries individually. So for example, binaries from factory A, binary for factory B, etc. And to allow for at-scale analysis, this phase needs to be automated. And its objective would be to dissect the binaries into comprising components, so the different subroutines, for example, and identify also the targets, the call targets between the different subroutines in order to reconstruct an as complete control flow graph as possible. It's also important to also visualize the results and allow for interaction for the results. Now, following this methodology, we have developed the Industrial Control Systems Reverse Engineering Framework, ICSREF, which is a modular Python tool. And you can find it on our account on GitHub. It's already available. Now, ICSREF targets and is able to reverse engineer binaries that are compiled with CODESYS, which is one of the three major platforms for ICS, along with Step 7 for Siemens PLCs and Studio 5000 for Allen Bradley PLCs. So CODESYS is more of a third-party tool that vendors can kind of license to their products, and they have been collaborating with more than 400 different PLC manufacturers, including well-known names like ABB, Schneider Electric. So it's quite prevalent out there. To give you a sneak peek before going into deep details, before analyzing a binary with ICSREF, it's just that. It's a binary. It's a collection of zeros and ones. Perhaps you can find some strings here. I don't know if you spend time staring at binaries at night. However, after applying ICSREF, we can see that we can dissect this binary into the comprising subroutines. So each node in the graph here is a different subroutine, a function. We can also see the edges that are calls from one function to another, find statically linked code, dynamically linked code. And going into more detail, this is the result from the manual analysis of the file format. You can see the memory map of a binary compiled with CODESYS here. On the top, we have the header, followed by some subroutines, and then static libraries, statically linked library code, user-defined code. On the right side, you can also see the different prologues, the prologue and the epilogue convention, calling conventions for binaries. Perhaps the most important subroutine here is this memory initialization subroutine, which is where the entry point of the binary is. So when execution is diverted to these binaries, this is where it actually starts from. And this subroutine is very important because apart from apparently initializing the memory for the entire binary, it also calculates the call table, which contains all the jump targets. So we can resolve all the jump targets and thus reconstruct the control flow graph for the binary. Now, part of the first phase, we also generate two databases. The first one pertaining to inputs and outputs, and you can see here the pop-up that shows up when you try to program a particular CODESYS device. This is a WAGO PLC. You can see the IOs there, whenever you have a read from that address there, the first one, that means that you're bringing in data from a sensor, and then whenever you have a write to the output, the second line, that means that you're sending back data to an actuator. So in our paper, we also describe a way that how we automated this process to extract this information in an automated manner from the CODESYS target files. We also built a second database that contains signatures of known library functions. So we use the concatenated sequence of opcodes to generate signatures for different functions, so as to avoid reverse engineering the same thing over and over again. This step is also automated, and we can append new signatures to our database. And we have at the moment around 1,800 different signatures for the libraries we have, and we are constantly updating it as we find new libraries. Another important module that ICSREF incorporates is the ability to have to extract arguments that get passed to different functions. So whenever you have a function to a function such as a PID, this is a proportional integral delivery controller, which is a typical control primitive. It's found in ICS. So whenever you have a call to a PID function, you have to pass in some arguments such as, for example, set points or gains, proportional gains, integral gains, etc. What we observed on the right side, manually annotated disassembly, is that these arguments get passed on the stack. Right before the call to that particular function, you would have to pass in and populate the stack. And by symbolically executing this, the binary up to the point of the call to the PID function, we can extract the parameters that actually get passed there. And that can give us contextual information about what the particular numbers are for the gains, for example, or the set points. To evaluate whether ICSREF actually works, we used in-house binaries that we developed in our lab, and also downloaded binaries from GitHub by searching for particular metadata that is stored along with CODESYS project files. So we found 471 source-coded binaries from different users that targeted different vendor PLCs. And after discarding code stubs or corrupted files, we're left with 266 binaries that we used for testing. And we did analysis of the control flow graph generated by our ICSREF tool, and compared it to the source code that we had available for these binaries to verify that everything worked correctly. In terms of performance, we can see here the breakdown of time spent based on the size of the binary for the 266 binaries that we analyzed. You can see the time spent in disassembling the binary with the DARE. This takes less than a minute for a larger binary. And on the top right side, you can see the time spent in anger for symbolically executing the memory initialization subroutine to generate the call table that I talked about before. This is linear again, takes between 30 to 40 seconds. Other operations are negligible, less than 2 seconds. So in total, the entire time overhead is linear to the binary sizes. A good thing in industrial systems is the fact that the binaries, to our experience, we haven't experienced a binary that's larger than 2 megabytes, for example. And that will take less than 5 minutes. And we could do this in parallel for analyzing each binary. Each binary could be done in parallel. So this scales well. We also instantiated a case study to show, so we wear a black hat and demonstrate an attack where we deploy ICSREF on a smartphone, a commercial smartphone. We also show that this is cross-platform because the smartphone has an ARM processor on it. The idea here is we have a threat model with 2 actors. So one actor is the attack designer that would is the mastermind behind the attacks, let's say, and then the attack deployer, which is a person that just introduces the smartphone inside the physical facility that's under attack. And ICSREF would be responsible for grabbing the binary from the PLC, analyzing it, and then generating a process-aware attack that's contextually relevant to the physical processes happening. And we see here that we targeted the Tennessee Eastman chemical process, the standard benchmark process, and in particular the reactor pressure. So with ICSREF, we're able to generate process-aware attacks by manipulating, for example, the proportional gain and settling at a lower point for the set point at 2300 instead of 2800, leading to monetary losses because of the suboptimal operation, and also to integral gain attack where we flip the bit of the integral gain and cause the error to accumulate, essentially leading to the reactor blowing up. And all these things are happening without any requirement for interaction with the command and control server. So the attack is autonomous because of the automated reverse engineering. To conclude, we propose a methodology for reverse engineering industrial control system binaries by taking advantage of the unique characteristics that the binaries have. And we also instantiate ICSREF that can reverse engineer CODESYS binaries. And we also make available the binaries and source codes that we were able to obtain from GitHub, allowing for experimentation. Thank you very much for your attention.
Hi, thank you for your talking. Alejandro Mera from Northeastern University. I have a question. The PLC that you showed there, the WAGO, is ARM architecture, right? Yeah,
here,
that one is
yes.
ARM, right? So did you find the same binary format for x86, for example, Backup or other brands?
That's a good question. So different PLCs use different ISAs. At the moment, our instantiation of the tool, ICSREF can only handle ARM compiled binaries. Mm-hmm. However, preliminary investigations show that the compiler follows similar conventions for compiling the binaries. So you could relatively easily translate the work that's been done here to different instruction sets. But at the moment, it can only handle ARM binaries.
Okay, thanks.
Hi, I'm Daniele from SUTD. Great talk. I was wondering if your toolkit is capable of dealing with anti-reverse engineering techniques, such as code obfuscation and encryption.
At the moment, as it is, it assumes that the code has been compiled with the compiler, with the standard compiler. So I guess if you tweak it, if you change the conventions, the calling conventions, then it wouldn't find them. However, those would still show up in the disassembly that would be generated.
Are you planning to include this functionality as a future?
That's very interesting. But again, it depends on the threat model you assume and what capabilities.
Okay, thanks.
If you cannot constrain what the attacker can do, then it's a very hard problem.
Hi, Malachi Jones from MITRE. Thanks again for reaching out, for responding to my email. It's a great paper, and I enjoyed the talk, so I've thoroughly read through it and everything. And I'm really interested in this area in automated reverse engineering. So one of the things that I wanted to ask you was, right now you're just doing the mnemonic to catch basically a hash of the particular function, but have you thought about expanding that using maybe some machine learning techniques to detect versions of a function, so maybe the library gets updated, so instead of having to run your tool every time to to get this unique hash, you can say, hey, this is a new version of this function foo. And so I'm just wondering where that's at on you guys' radar.
Yeah, no, that's very interesting. We designed the whole thing to be modular, so to allow for swapping the different modules in and out. So we're thinking about whether you should have something more intricate, like machine learning for detecting the functions. However, when we tested this hashing technique, it seemed adequate at the time, but it would be a very interesting idea to explore.
Yeah, if you have any questions, because that's what I have that's what I do a lot of, so you can reach out to me. You have my email, so
we do, yeah, thank you very much.
Hi, Fish Wang from Arizona State University. I really enjoyed your talk and your paper. I read through it, and I think it's really good. Can you please go to the next slide, or the slide, the one you have several diagrams on how much time is taken in each stage? Yes, this one. So I wonder, it seems to me that your approach, especially the anchor time, you are using that to recover the call targets, right? It seems to me that what you really need is a way to emulate the execution, not really symbolic execution. Can you please tell me, give me some more, what do you think of, using symbolic execution instead of using a simpler simulation on this?
So we deploy Anger in particular because it can handle the concolic execution as well. So it would constrain itself when it comes to that. So emulation could also work. However, I'm not sure because some of the memory is not initialized when we try to jump to that particular address. So you might run into some problems there. So I mean, anger seemed to work, and the time that was spent was adequate, so we didn't really look into the emulation part that much.
Yeah, so the reason why I'm asking this is that, we made anger, and the anger is not very fast. We profiled it yesterday.
30 seconds is.
Yes, so we realized that we were doing a lot of things that are not very optimal, and then we were spending a lot of time in things that are not really necessary to do symbolic execution. It seems to me that whenever I see people applying symbolic execution on things, they are spending like 100x times on what actually should be taken if you're using emulation. That always seems to me that maybe if you don't use anger, if you use something else, or if you use another approach, it might be taking a lot less time. This is just my view. Thanks.
No, I understand. I'll reach out later to discuss the emulation possibilities. Thank you very much.
We have a branch for you that's 40% faster already from yesterday. Looking forward to talk to you. Thank you.
Thank you very much. Let's thank all our speakers.